Alright, so we've handled or assigned an unscientific definition of temperature, and then with the zeroth law we've developed a more scientific determination as the property that is the same when two objects are in thermal equilibrium. Now we want to connect this to a more deeper understanding. Thermodynamics. Thermodynamics is the field where we study energy and its connection to the microscopic world. And we're going to develop scientific definitions for the properties of temperature by considering how energy can be stored and transferred at this microscopic level, taking into account the atomic nature of matter. The first thing we're going to define is internal energy. An object internal to itself, due to the fact it has atoms and molecules moving around, interacting as if they're connected by little springs, has energy stored in it. So all energy is made up of these atoms and these molecules. And previously, when we considered like a block on an inclined plane, we ignored all that. We're not going to ignore it now. We're going to count up these energies. So the good news was before we had worked non-conservative and we swept things under the rug. The bad thing now is that we're not going to have any rugs to sweep under. We're actually going to count up all the energies. So the definition of internal energy is simply the sum of all the kinetic and all potential energy of the molecules that make up a system. So, we had these blocks, and now we're really going to consider the fact that they're moving in here, little atoms that has kinetic, and potentially these guys might be connected to each other by like little springs. And we need to add up the energies of potential and kinetic that are going on inside of here. The units for measuring these things are the units of energy, so they're the joule. Later on, because these are such small energies, we'll learn other units, such as the electron volt. Now, let's take a look at something real simple. The simplest thing, what we'll eventually talk about as being an ideal gas, is to consider the gas to be composed of little billiard ball like particles, and that these particles and all their properties can be described using Newton's laws and considering them to be moving along with speeds and therefore having kinetic energy. So all your gas laws and everything else will eventually be able to get by just considering these guys to be going in a wild bunch of motions here, flying around like that. And if we wanted to know the internal energy, we could, in theory at least, simply sum up the energy of each one of these little particles. So we could add up the energy of the first particle, the energy of the second particle, the energy of the third particle, and so forth. Now, if you've had chemistry, you may remember that even in a few grams of such, like for instance 12 grams of carbon, there are a large number of molecules. In fact, in 12 grams of carbon, there's Avogadro's number of molecules, 6.02 times 10 to the 23rd. So it's conceptually possible to do this, but obviously we don't find the energy that's internally stored by summing up these, because A, it would be difficult to measure the atoms individually. We're going to find out, in fact, it may not even be possible to talk about an exact energy if you go further on in modern physics, and the fact there's so many of them. So not practical. To add up the individual molecules' energy. But we can conceptually do it. And what I'm going to do is I'm going to relate it to something that we can measure and find the total energy all at once. And it'll be an old friend, something we've already considered when I get to it. Now, In thermodynamics, there turns out to be two types of properties that we talk about a system. We talk about extensive properties and intensive properties. And usually we want to describe systems in terms of their intensive properties. So let's discuss what that means. Let's say that you had an object like this. Could be a block or something. And I was to go along that block, for instance, and split it into a smaller block. So originally I had the big block, and then somebody decided just to come and take only that part of the block right here. Would the second block have the same reading for mass as the first block? No, because I have less of the stuff. If a property depends on the number of atoms in the system, then that property is said to be extensive. So an extensive property of a system are properties that depend on how many atoms are in the system. So if I take the green to be my system, I have more atoms than if I cut and only take part of the block. So the mass of the system depends on the number of atoms, therefore it's an extensive property. If you were counting up the energies that we had before, for instance, you had this particle going here and this particle going there and that particle going there and this particle going there, but there are particles over here, then if I cut and only consider this part, I'll have less energy than if I took the whole thing. So internal energy is also an extensive property. That is, it depends upon the number of atoms, the system. If you increase the number of atoms of a system, you'll increase the internal energy. Intensive properties are properties of a system that do not depend on how many atoms the system has. So let me show you an example of one of those. Let's say that you had water in this, and we happen to know that the density of water is 1 gram per centimeter cubed. And if you only took this half of the water, the density would be 1 gram per centimeter cubed. If you took only that water, it'd be 1 gram per centimeter cubed. If you took all of the water, it'd be 1 gram per centimeter cubed. It doesn't matter how big the object is. Another example of that is temperature. If you put your thermometer in here, and you're at 100 degrees C, and you put your thermometer in here, read 100 degrees C. If you split it into two pieces, you'd still measure 100 degrees C. Actually, I guess we couldn't measure 100. How about 30? If we measured 100, we'd be measuring steam. All right. So temperature and density are what are called intensive properties. They don't depend upon the number of atoms in the system. You can convert an extensive property to an intensive property simply by dividing by the number of atoms. We usually give that symbol, the number of atoms, an N. Sometimes it's somewhat script, like this in books. Most of the time it's just a straight N like I drew here. This lets us get the idea that we might want to create what's called the average energy per molecule. And when we go to these intensives, we usually use smaller letters. So I use a small u instead of a big U. So this small u is defined as the internal energy divided by the number of atoms, or number of molecules. So as an example, let's say that you had the ocean here, and you reached in here with some sort of a cup, and you pulled that cup out. So there's my cup now. And so now I've got water. The temperature of the water in the cup would be the same as the temperature over here of the ocean. But the energy contained in the cup of water, the internal energy of the cup, would be much less than the internal energy of the ocean, because the there are a lot more atoms moving around with kinetic energy in the ocean than there is in my cup of water. So, although the temperature can not be very high, the ocean can contain a tremendous amount of energy, it turns out, because there's so many atoms. So, average energy per molecule is an intensive property. Now, let's consider what happens when you stick two objects who have completely different energies, average energy in molecules. So, for a minute, we'll just think about kinetic. This guy, let's say, are going really fast. They have a lot of energy on average. You can think of them as people with $1 million. Each one's got a lot of money. And then they're banging now, interacting with an object over here whose particles are not moving very fast. So this is high U, and this is low U, where U is the energy per molecule. When this fast-moving object hits a slow-moving object, the fast-moving object begins to slow down, and the slower-moving object picks up speed, just like an object running into a second ball in a pool game. So, we know energy is neither created nor destroyed. These are elastic collisions. So when this thing hits, if this one loses energy, the energy it loses goes to the red atoms, which pick up speed. So this U is going to go down, while these U's are going to go up. Now at some point, this thing reaches thermal equilibrium. We know that. Said that earlier. So what does that say the condition has to be in terms of the energy? Well, what has to happen is eventually the energy transferred has to stop. And that means that these particles' average energy has to reach those particles' average energy. So thermal equilibrium, another way of saying what thermal equilibrium was, is that the average energy per molecule for both systems has to be the same. If this guy's moving with 1,000th of a joule per molecule, this one has to be moving with 1,000th of a joule per molecule. These guys will keep stealing energy from those guys until these guys drop down to the same value that these guys have risen up to. But we said thermal equilibrium was meant the same temperature. And now we're saying it has the same energy per molecule. So there is a relationship between the average energy per molecule, just colliding billiard ball conservation of energy and momentum, in collisions. And an object's temperature. So what that tells us now is temperature is directly proportional to this average energy per molecule U, or put another way, if you want to calculate the total internal energy, it's proportional to the number of atoms times the temperature. Not equal, proportional. We'll have to find a proportionality constant. So instead of measuring those atoms by adding them up one at a time, what I'm going to do is I'm going to use a thermometer and determine the number of atoms. I could do that using Avogadro's number, densities and things like that, and a scale, and I can determine the total internal energy. All right, that covers this portion of Thermodynamics 1.